Okay, so if it looks like there aren't going to be any more people showing up, I'll just go ahead and get started. I'm going to share my screen now. Okay. So the main thing that we're going to talk about today is something called autocorrelation or cross-correlation, which is just a way of testing to see whether one signal contains another signal. So just like to quickly go over some of the stuff that was important that I talked about last time that's going to get talked about again today is that the most important idea in all of digital signal processing is that all signals, even continuous time signals, are basically vectors. And the reason why that's useful is because it lets us define dot products between them. And that lets us have a very natural way of answering questions like whether one signal contains another or how much of one is in another. And it lets us do operations familiar in vector arithmetic for like just changing a coordinate basis. Like when you do a Fourier transform, you are essentially just changing the coordinate basis of a continuous time signal to sines and cosines rather than just amplitude as a function of time. So this lets us say that, like, if we have two of these weird function vector things, we can define that, the dot product between them, as the integral of their product over some range. And then this definition works in both the time domain and the frequency domain. It's just a very general construction. And this, so the dot product is essentially, it is the way that you ask how much of one signal is inside of another. So we did this with sinusoidal functions last time to derive the Fourier transform. Now, now we can do it with an arbitrary like template of a signal that we're looking for to see whether whether a signal that we are reading in real time contains a specific feature. So first, if we have some function, like some signal that we're actively computing its Fourier transform of, and then we just look at the look at the magnitudes of the frequency. And let's say we have a spectrogram that we're computing in real time. So, so like for that signal, if it's just like a constant signal, that'll look something like that. Then let's say if we have a spectrogram of a feature that we're looking for, say one of the projects was looking for syllable recognition. What we can do is we can use this same definition here to test whether the live signal that's coming in contains like some feature that we're looking for. And we do that by, if we store I need to scroll out. Okay, so if we store in a gigantic array, just in memory as a 2D array, the spectrogram of the audio that we're actively recording, where on one axis we have time, and on the other axis we have the frequency, and the values in the array store the magnitude of the frequency at each point in time. So like vertical slices out of this array, just the columns, would be individual Fourier windows that we've calculated over time. And then let's say we have a previously recorded signal that we are looking for inside of this one. So in the case of syllable recognition, this would literally just be a recording, I'll call it T, of omega and time, like just an audio recording of something we're looking for in this signal. And this is referred to as the template, and it has the exact same form of this array that we're storing all of our frequency data in. And if we want to test whether f of frequency and time contains our template of frequency and time, what we do is we multiply. The Zoom UI is getting in the way now. Okay. We multiply together every single corresponding element of these two arrays, and then add the result together. So what this is doing, dot, all of them. So like item 1, with item 1 in each, item 1, with item 1, in each, so on and so on. And then just take the sum of all of those products. So what this is doing is it's treating both of these frequency, like both of these spectrograms that we've computed. It's technically just treating them as really big, long, stretched out vectors. Like if we just put the Fourier windows back to back like this in a single huge long vector, and then it's taking the dot product of each, using like this definition right here. And then what that does is it's telling us how much of f of omega and t is in the direction of our template, where the dimensionality of that space is equal to however many elements are in each of these arrays. Now, there is one thing that's important to do here, which is before we do that operation, we have to make sure that both of these arrays are normalized. And the importance of that is just to make sure that if I just play random noise into, if I just see random noise and I do this operation on it with a template, what will happen is it will probably yield a fairly large value that would suggest that the two signals are correlated and that there's a lot of the template in it. However, what's actually happening is you're just filling the entire f of omega and t with really big spurious values, which just makes anything that you do when you're calculating the sum be a really big value. So you normalize them first before you do this operation, and it makes it so that only the parts of these two signals that are actually sharing similar frequency and time actually multiply together and produce big values. And it also makes it so that the result of this operation returns a simple value between 0 and 1, depending on how correlated the signals are. So I have an example of the implementation of this. So this is called cross correlation. And here I have an example of how you would implement this on Arduino. It's fairly straightforward. So all that really happens here is in our main loop, we just, so this is just some stuff for setting the template. We'll ignore that for right now. All that's really happening is we are just furiously recording audio all the time. we are calculating the Fourier transform of the data that we're currently receiving, like of the audio that we're currently recording, which happens in process data, where all that happens is we just, similarly to the code I showed you guys last time, we just load all of our sample data into vReal, set the imaginary to 0, call these 4 functions to do the Fourier transform, and then we add that resulting Fourier transform to a gigantic 2D array containing frequency magnitude data as a function of time. So like the first index is the time, and the second index is the frequency, and then the value at each point in that array is the frequency magnitude. So we're just calculating that constantly for the incoming audio stream. And then when we want to test whether the template, like whether the data in there matches the template, what we do is so in the original main loop, we process the data as soon as we get enough samples to do a Fourier transform, and then immediately check whether it meets the template and evaluate template. All that does is, so the template is stored as a 2D array of the same size as our frequency array. That doesn't necessarily have to be the case, but it just makes it conceptually easier here, where this has the same form, where the first index is time and the second index is frequency, where an index of 0 in here would be the most recent time in the template, and an index of frequency when count, whatever that works out to up here, that would be the latest time. And then FFT 0 to FFT win size over 2 goes from 0 to our sampling frequency over 2. And then when we check for the correlation, all we do is we just define a variable correlation, and then we iterate over both arrays and add together each corresponding, multiply together each corresponding product, each corresponding element, and then add that onto the variable we just defined. And then at the end, divide that variable by the product of the sums of both of those arrays. And that's where the normalization happens, because you know that like all of the elements, so both of these sum variables are just used to store and calculate the sum of all of the values in both the template array and in the current audio, like recorded audio array. And then we just divide by each of those at the end to make sure that we get a value between 0 and 1. And then that, after that, and then this function, it doesn't return the actual correlation, although you probably will want to if you decide to go with this implementation. It just returns whether the correlation between 0 and 1 is greater than some predefined threshold, which I think is 0.5 up here. Yeah. And then the general idea is that this just constantly records audio, and every single time it has enough samples to calculate a Fourier transform, it does that, and then does this weird sort of dot product-ish thing between the all of the Fourier transforms of the last few seconds of audio with a desired template of a pre-recorded signal. And then if the result of that operation exceeds 0.5, we consider that to be a positive detection. The signal contains the feature we're looking for. And actually, before I show this, I'm going to first verify that my Arduino is actually streaming audio correctly. So yeah, a quick disclaimer. So this code, this will only work right now on SAMD51 boards. I think you guys said you're using ESP32s, is that right? Okay. So this will only work on SAMD51 boards. There are analogous libraries. So the main dependence is on this SAMD timer object that I'm using. There is an analogous library for, which is, I think is called ESP32 timer interrupt, where everything is exactly the same, except the class definition is slightly different. But if you just substitute out this declaration with the correct one from this library and substitute in the, including the library, all of this code should work perfectly fine on an ESP32, plus or minus like changing your audio input pin to whatever it's supposed to be, as well as your serial rate, like baud rate, and your analog read resolution and all of that. And again, this timer is the way that I'm recording audio, where I'm using an interrupt routine where this will just automatically fire off an interrupt every however many microseconds I need between samples. And then every single time that interrupt happens, it calls this function to record a sample to the volatile input sample buffer. So yeah, I've just uploaded this other simpler program, which should just let me view the audio feed from, the serial monitor is open. This should just show you guys the audio feed from my Arduino right now. Yep. Okay. So the axes are pretty, it is a little noisy, but that's just because we aren't using, our application doesn't need noise gate thresholding stuff as much. So it's just the gain is ridiculously high right now because the input signal level is so low. But so yeah, this is for the Pied Piper project, and our project involves contact microphones rather than regular microphones, but all of this should still work the same. The only practical difference for this demonstration is that I will have to wedge this microphone against my neck to get it to actually perceive a signal rather than it picking up my voice through the air. So there you go. Okay, so now that I know that the audio is working fine, I can re-upload this. And then this should hopefully demonstrate how we can, so yeah, the last thing that's going on here is the template in this program is just some pre-recorded, or not pre-recorded. So if I call this set template function, what it does is it just sets the template to all of the stuff in the frequency buffer. And that just makes it so that I can record an arbitrary template whenever I feel like it. And oh, that has uploaded. Okay. Oh no, not the plotter. Oh, right. It's firing off lots of positive detections because I haven't set a template yet. Okay. So, yeah, one more disclaimer. This code, I outlined it Friday evening and wrote it in a blind panic an hour and a half ago. So hopefully this works. But the general idea is now I've set a template. It was just me humming a few seconds ago. And what should happen is when I start humming into the microphone again at the same tone, if I don't know how precise I need to be. What should happen is as soon as enough of that hum gets through to for the signal to look like what the original template looked like. When this evaluate template function gets called, the result of like multiplying together each corresponding elements of those array and adding them all together and dividing by the total sums, that should produce a number bigger than 0.5, hopefully. I also might not have set the template right. Okay. Oh yeah, so this code, so how do you guys want me to share this? Should I like make a GitHub page for it, or should I just share it through Basecamp or something?
It does work for me, I think.
Okay. Yeah, I'm now dreading that I might have made a mistake in here somewhere. Yeah, okay. Well, anyways, do you guys get the general idea behind this of like multiplying together? Like if you want to check whether, oh, okay. Yeah, so like, do you guys get the general idea of multiplying together corresponding elements of stored frequency data in just a couple of gigantic arrays and then adding those results together to get a number that shows how correlated the signals are?
Yeah, it makes sense. Definitely gonna have to play with it before knowing how to use it. But, yeah.
Okay. So I can actually, all right. Okay, that's fine, Nick. So yeah, I'm now actually going to talk about some of, so this is the most straightforward way of testing for whether a signal contains an arbitrary feature. The main problem that this runs into is what happens if the feature you're looking for can vary by any amount. So this method, it will work perfectly fine if like if you know that the feature you're looking for is going to be exactly the same every time. So this is the method that's used in like radar and things like that, because you know you've sent out a really specific waveform with a really specific frequency distribution, and you're going to be seeing returns of that exact same thing. But in the case of like testing for features of a human voice or something, this can run into problems because just because things like the tone of someone's voice can vary by a tiny amount, and then that can throw this off. Because like say you're even just in the simple case of testing for a simple tone, just a sine wave that on a spectrogram just looks like a stripe across like that. If the sine wave that you still want to be seeing is off by just a tiny little bit, like it's higher in frequency by just a tiny little bit, then what happens is the product of these two matrices is now close to 0, because each sine wave just makes a really sharp delta function that just gets stretched out over time. And then when you multiply corresponding elements of these two matrices together, what happens is you'll get to the sine wave in the template and it'll get multiplied by nothing in the audio you just recorded. And then you'll get to the audio you just recorded, like the sine wave in there, and it'll get multiplied by nothing. So a tiny difference in the frequencies, like the tone of the signal you're looking for, can completely throw this off. There are some ways around that. So one way is, Okay, yeah, so you can set the threshold to be lower. In this particular case where we are just looking for a pure sine wave and we get a pure sine wave of a very slightly higher frequency, that wouldn't work because they would just evaluate to close to, like very close to zero anyways. But if you have something like a feature that that has different parts of it that don't always show up. So for example, like I can actually use an example from the Pied Piper project where we have these mating calls where I might be able to quickly pull up an example of one. Or, okay, that'll take too long, we'll just sketch it. So we're looking for mating calls, which on a spectrogram, like the parts that have a lot of energy, where, okay, what just happened? Okay, I don't know what that was. So we're looking for mating calls that look something like this on a spectrogram, where they just sort of rise in tone and plateau after a little while. Sometimes these mating calls can also have higher frequency chirps that are intermittent through them. And those aren't always there. So if we were going for the template approach, and let's say we were absolutely confident that this tone in the middle here was at the exact same frequency every time, then what we could do is we could get away with just setting a really, like a somewhat lower threshold of probably like 0.2 or 0.3. So that when we test this signal against a template that only contains this main frequency part, these extra high frequency chirps won't, they won't throw it off that much because they just, like they won't, like it'll lower the correlation value by a little bit because when the audio we've just recorded gets normalized, that extra energy in the high frequency chirps would cause the main sine wave part of the signal to be smaller in amplitude, but it would just give us back a value that's, it would just give us back a correlation value that's still high, but just a little lower, and we could deal with that. So the main problem with this method, as I mentioned before, is if the main feature you're looking for varies in frequency by a tiny little bit, then it basically just breaks, and you just won't see the feature show up. Like this dot product operation thing will just never produce a very large value. So one way to get around this is to just use lots of templates where why does it sometimes decide to scroll and sometimes decide to draw? Whatever. So you can use multiple templates where if you have several different examples of what you expect your signal to look like, you can test the correlation against several different possible templates for what it could be. However, that gets that can get really cumbersome really fast, especially when you know when your signals, when the feature that you're looking for isn't going to, like, it's going to vary by some continuous quantity. Like I would expect the sine wave over here to be in some range. And then I don't want to have to include a template for an example of the sine wave in every single iteration of one of my frequency bins. And that can get, yeah, that's just, this gets very memory intensive very fast, and also computing the correlation can start to take too long. Because if computing all of this stuff, including the Fourier transform, starts to become longer than it takes for you to record one Fourier window worth of samples, then you lose the ability to execute this in real time, which is obviously a problem. So the other approach you can do is, rather than have a million different templates that you test against, you could have one, you could just have one template where you've essentially, where you have a bunch of examples of your signals, of like different, just different ideas of what the signal could be. And then you basically just take an average of all of those templates and store it all into one. So this is, at this point, this is technically, very technically light machine learning, but don't go around calling it that because people will get annoyed at you. Where if you just have a million different examples of what your signal might look like a million different examples of what some specific syllable might look like. What you can do is you can either just average all of them together and hope for the best, which can actually work surprisingly well a lot of the time. Or what you can do is you can set up, so you can figure out what average-ish template you need to have by doing, like essentially by doing very light, slightly less light machine learning, where you you start out with just a giant array of like one of just some constant value that's just 1 over the number of elements in the array, so it's still normalized. And then you use an algorithm called gradient descent to figure out what each element of that template needs to be in order for it to be able to maximize the correlation value that it reads off if it is applied to every single one of your examples independently. So I guess a good way to initialize this template would be to actually start with one of the spectrograms of your recorded examples, and then figure out, essentially map out the space of what the correlation value works out to for, as a function of like how much you change each of these values individually. And then just, okay, I don't know how to draw however many dimensional graph that would be, a 64 dimensional graph, but the general idea is you do something, gradient descent is an algorithm where you just say that you imagine all of these points as being in a, you just imagine that there exists some function of all of these values in your template that you're trying to make. And then what you're trying to do is you are trying to find some set of these constants where hang on, so I should first ask, are any of you guys familiar with gradient descent already?
I'm not familiar.
Okay. Oh, okay, fish to us, okay. Okay. So I'm not going to try to talk too much about, oh, you have taken a machine learning course. Okay, so then this should be, for Vishnu, this should hopefully be straightforward enough, but I'm not going to talk too much about, okay. Yeah, I'm not going to be able to talk too much about what the algorithm is right now, but It's conceptually fairly straightforward, where it's just a very abstract way of essentially in this particular application, what we're doing is a regression, where you know how when you have a bunch of lines, like, or you have a million points on a graph, and you want to find a line of best fit through those points. What you're doing is you are finding a line that minimizes the total error between all of your points in that line, or specifically the error squared. So you have, like, we're trying to fit y equals mx plus b to all of these points. And we're trying to, what we're doing is we have an error function, which is a function of our parameters for the equation. And that is equal to the sum over, so let's say these points are just x1, x2, x3, on and on in a sequence. Or hang on, I should not define that index like that. So we, let's just go K. So M
يمسح اسهل مسار فهو ما راح يدش على هذا يمسك فوق وينزل على الباقي. اوكي يعني نحط فيها شيء انت الحين هذا زاد.
Okay, so the general idea with this error function is that we add up the total area or the total error between our current two parameters that we've chosen for this line, and we square, like specifically the square of all of that error. So like if we plug each x value for each point into our equation, and then find the difference between that and the actual point, and then square that error, add it up for all of them, that gives us the total error of our current best fit model to the data. And then what we do is we want to find some algorithm that lets us find parameters m and b such that that error is minimized. And the way that you do that is through gradient descent. And gradient descent essentially says this error function, which is easy to talk about for this 2D data here, or okay, technically 3D data, but this error function with two parameters in this case, we can think of it as a 3D surface. I'm gonna have to try my best to draw this in a way that makes sense. Yeah, so this error function is a 3D surface where our independent variables are m and b, and on the up and down axis we have the error. And what we're trying to do is find a minimum on this, in this error function for some m and b. And then that will tell us what our line of best fit is. So this algorithm can be extended to this template that we have up here, where rather than just m and b as our parameters, we have many more parameters. We have one for each point in time and frequency. And our error function is the so rather than having an error function, we have a function that tells us the correlation that we get for each of our examples. So we would want a function that maximizes the so we ideally we would expect our template to produce the highest correlation value possible for every single one of our examples that we feed into it. And the way that you do that is by extending this error function thing over here to just have many, many, many more parameters, one for each element in that gigantic template array. And you, the error function isn't really error anymore. It's the sum of all of the correlation values. And the way that you minimize these parameters is you do something called gradient descent, where you figure out how the error function changes as a function as you move along each direction for each parameter. And then you just continuously move along the gradient or down the gradient until it stops going down. So obviously that won't get you the best set of parameters all the time, but it can get you better parameters. So I don't have, there's lots and lots and lots of nice, concise, like conceptual overviews of how you go about implementing all of this. So this is not something you would do in real time on your Arduino. This is something you would like pre-compile a template for the types of signals you're looking for on your computer using a bunch of examples, and then you would upload that template to your Arduino to do your dot product thing. So today I'm not going to have enough time to go over how to talk about like actually how you implement the code and algorithm and everything for figuring out the ideal set of these points for your templates, but like I can talk about it next week if you guys want. And there are online, there are a decent number of like nice, simple conceptual overviews for how gradient descent gets extrapolated to like arbitrary data sets like this. So I know last week I told you guys stay away from machine learning for the love of God, but this, I realized that this actually, for the types of problems that you guys are dealing with, it is actually a good idea. Because like the features, this sort of template thing where you compile a template from a bunch of examples and figure out what each value in it needs to be in order to maximize its correlation with each of those examples. That is actually the simplest way that you guys could go about reliably implementing an algorithm to do most of the things you want to do, because it's simply because human voices can vary a lot, and like actual real signals, like we benefit a lot on Pied Piper from the fact that the mating calls look almost exactly the same all the time. So we can just check to see if there's a lot of energy in a specific frequency band after doing all of our like time and frequency smoothing and whatever. But if you need to recognize a bunch of different types of signals, where you have some class of feature and it can have a bunch of different possible appearances, then this is the only realistic way you could go about doing it reliably. And yeah, so would you guys want me to talk a little bit more about gradient descent and how you figure out how to make an ideal template for a bunch of signals?
I mean, I think it's pretty interesting. Yeah.
All right. So yeah, next time, like I will, as soon as I figure out what's wrong with it, I'll post the code that I showed you guys over here on the Basecamp. And then next time, I should hopefully have an example ready of how you go about making like an ideal average template for testing a million different examples of a feature. To average out different templates. So yeah, that is an option. So that is sort of something I was talking about before, where if you don't want to go through the mess of gradient descent and you know for a fact that the features you're looking for are going to be like, they're not going to benefit from this very much, like they aren't very complicated, then you could actually literally just average out a bunch of templates of different examples of the signal. And that would, if you're willing to occasionally tolerate like false positives and false negatives, that would be perfectly fine. But if you want to do it like the whole idea of this method is it gets you literally as good as you can get for this simple template method. And if you don't need absolutely as good as you can get, then yes, you can definitely just average a bunch together and then use a low correlation threshold. So for example, like if for this signal, if I had a bunch of different examples of this signal where all of the sine waves just varied by a little bit by a small amount, then both the result I get from gradient descent and the result I get from averaging stuff would just be like a faint mistiness of somewhat low values in the general area of where those sine waves can be. And then I would have to use a lower correlation coefficient to actually recognize my signals. Although this would also be prone to getting thrown off if I had a signal that was like rising or falling in time and it crossed through that region for long enough, then it would confuse it. But yeah, you can it is an option to just average together a bunch and then use a low correlation coefficient.
Awesome.
So yeah, that's all I really have time for today. Hopefully by next time I should have an example of gradient descent and making an, oh yeah, I'm gonna post the code as soon as I debug it. I had to write it immediately before class, like an hour and a half ago. And it compiled, so I assumed that was all magically working correctly on the first try, but it looks like it wasn't. But there's nothing overtly wrong in this. It's like I probably just have a index the wrong way around somewhere, or I'm not iterating this properly somewhere. But yeah, I'll upload this to Basecamp as soon as I get it working.
Awesome. Really appreciate that.
Okay, so yeah, hopefully, do you guys have access to MATLAB?
Yeah, but so.
Okay. So when I do my gradient example thing, gradient descent thing, I'll probably implement it in MATLAB just because it's basically built for doing stuff like that, and it's really easy.
Cool.
Okay. I'll see you guys later.
All right. Thank you.
Function